Hello, I'm Prathmesh and I will be presenting our paper Learning Class and Domain Augmentations for Single Source Open Domain Generalization, which is accepted to the Winter Conference on Applications of Computer Vision 2024. In this paper, we have addressed the problem of single source open domain generalization. So moving on to the introduction of the problem, we know that even though the deep learning models have demonstrated great results in classification tasks, they are built under the assumption that the training and testing data has been sampled from the same distribution and share the same label space. Any deviation from the above leads to significant degradation in performance of the classification model. The domain generalization deals with the violation of first assumption where the training data from multiple domains is available but the target domain distribution is different from the training domains. Another practical version of the domain generalization is single source domain generalization where only one domain is available for training. If we look at another practical scenario where the second assumption gets violated, this is called open domain generalization, where there are multiple domains available for training which may or may not share a label space, and the target distribution has classes which are not part of the label space of any training domain. An even more realistic setting for this problem is violation of both the assumptions stated above, that is, availability of only one source domain for training and presence of novel classes in testing data. To solve this problem, we need to build a model which will correctly classify the test samples which are from the training data label space as well as detect the unknown classes. Moving on to the methodology we have used in this paper, we have proposed an architecture called as SODG-NET. This has a classification head of size C plus 1 where C is the number of classes in the source domain and C plus 1th node is corresponds to the novel or unseen classes. In this architecture, we propose a style synthesis block to generate image features for diverse domains, and a feature aggregation block to generate pseudo-open sample representations. We recognize the fact that the statistical features extracted from various layers of the vision encoder contain domain-specific information. The style synthesis block over here uses these statistical features from feature maps extracted from two images from source domain belonging to the same class. These features are injected with noise, sampled randomly to have diversification in generated output, and are passed through the fully connected network to generate new statistical features. These new features are applied on the normalized feature maps of original image, which changes the domain information in feature maps without changing the content information. We employed a novel margin loss function to ensure the generated features are not very close to the original features. The loss LSM, as shown here, ensures that the distance between generated and original mean and standard deviation is always between A and B. This updated feature map with new style information is passed through the rest of the classification network with the same label as that of the original images. Our second addition to this classification work is the feature aggregation block, which is used to generate pseudo representations for open set samples. So this feature aggregation block is a fully connected network which takes input of the content features extracted from CNN encoder for two images belonging to two different classes to generate a weight vector alpha, which is used to combine content features of two images belonging to different classes in the source domain, which were also the input for this feature aggregation block. We also perform this combination with the content features extracted from the feature maps generated from the style synthesis block to ensure domain diversification in open set representations. These new features are used to train the classifier for the unknown class, the C plus 1 class, and they create a unified representation for open space which does not belong to any of the known classes. And so this was the complete architecture we have proposed in this paper. Moving on to the loss function. To update the architecture proposed, we have employed a set of intuitive loss functions. The first loss function is the cross entropy loss function followed by a discriminatory loss, which assists the cross entropy loss function in its job. This discriminative loss function targets the entropy of predicted distributions for open samples to improve the classification confidence and increases the gap between probability of closed sample being predicted as unknown and the highest probability from it in closed label space. This ensures that the closed samples are not misclassified as unknown. The third loss function is the margin loss, which I have explained while talking about the style synthesis block. We update our model by minimizing the sum of all these three loss functions. We have shown an ablation study by setting WDISC and WSM as 0 to show the importance of these terms in our in performance of our model. Moving on to the results, we have performed our experiments on various data sets. So here are the results on Office 31 and Digit dataset where we had used 10 out of 31 and 5 out of 10 classes as known and rest of them as unknown target classes. In the table, we can see that our method outperforms the literature available by 0.94 and 13.2% for the two dataset in the same order in terms of the H score. The TSNE shows a features generated on the test domain for the Office 31 dataset by our model. The credit classes represent the unknown classes, and we can see a significant clustering for known classes while the unknown classes falling in the open space. To validate our performance by the style synthesis block, we replace it with the domain generalization method proposed as mixed style, and a considerable dip in the clustering and arbitrary spread of the unknown classes is seen over here. Moving on, here are our results on Office Home dataset, where 15 out of 65 classes were trained as known classes, and the table shows results after using each of the four domains as source domain and keeping the others as target. On an average, we have an improvement of 2.19% in average accuracy and 7.03% in the H score. We conducted an ablation study by changing the number of known and unknown classes to find out that our model performs similar to MEDA and when cross matches are applied over MEDA in terms of average accuracy. While in terms of H score, which represents the balance between known and unknown classes, unknown class classification accuracy, we outperform the other two methods for smaller number of classes and move on to perform similar to other two for 50 known classes and above. Moving on, here are our results on the PAX dataset where 4 out of 7 known classes were part of the source domain level space while others were in the test data. Similar to Office Home, here we have used four source domains individually and others were as target domains. And while looking at the average performance, we can see an improvement of around 11% in the H score from the highest in the literature. So to conclude, in this paper, we have proposed an end-to-end architecture which tackles the problem of single source open domain generalization. We recognize the domain information in the feature maps of images use the images and use the style synthesis block to generate diverse domains. We generated pseudo-open sample representations using a learnable method to get a unified representation of such samples. And through extensive experiments on diverse datasets, we have validated the perform a significant improvement of results by our model over the literature. Thank you.